Welcome to Library Search for Non-Targets with Unknowns. The scenario we're talking about is quantitation with targets, and then you want to investigate an interference. You want to use tools like library search, and we've got an application with unknowns that can help you identify the target and the non-target. A more elaborate presentation of this is the quantitation workflow over here with the targets and the fact that we're going to use unknowns. And the key ingredient here is the fact that we're going to library search, for example with the NIST, and look for hits, characterizing them as either target or non-target, and coming out with potentially tentatively identified compounds. In order to control the libraries along with the parameters that are used by unknowns for library searching, we have the library method. The library method will direct, as I said, the libraries and potentially retention time constraints and the parameters so that library search returns those non-targets. So here is an example of a library method. And you can see that it searches first a smaller pesticide library and then looks in the NIST library, searching multiple libraries. So let's see a demo of library search results to investigate interferences, and I will pick two compounds and then show you how to go from Quant over to an application called Unknowns and see the results there to investigate this coelution situation. Let's take an example of using library search results to figure out that two compounds interfere with each other. So I'm going to pick the case of chloropyrifos and parathione, which do have ions which interfere. 125, for example, is shared between them, and they do coelute. Alright, let's start up the demo. I have two samples, a blank and a sample, and I go to the library menu and I start up library search results. Now this is going to use up some CPU time, and it's going to take those two samples, the blank and the sample with the targets in it, and it's going to start up deconvolution. Now deconvolution is a peak detection algorithm that is able to separate compounds that coelute by grouping the ions together that form the same shape. And once that deconvolution algorithm has accomplished creating the components, then each of those components will be searched against the library. Now the components that are created, it's not an exact science like extraction from quantitation. It's like putting on a different pair of glasses. But the usefulness here is that all of those components that are found are then searched against the library. And in this case, I've got both the pesticide library, which I've created from my targets using a calibration standard, and I've got the NIST library. So I can pick up the possibility of a component that's not on my target list. So this would be called non-target analysis. So the additional steps that will follow here is that once library search has been finished, since I have a blank that I've carried across, it will subtract any of the hits that are found in the blank so that I don't spend my time looking at something that has appeared in the blank. I've figured that the blank is clean. And then the last step that will take place here is target match. So target match is going to take my quantitation method and all the targets and the target information, including the retention time, and it's going to match those up against all of the components that were found and then mark them as either targets or non-targets. So we'll see the presentation come up here after it does the target match, and I'll explain to you what it's found. Here we are. Alright, let's take a look at the results. First, the blank. I can see that I've chosen the hits, and from the NIST library I've got lots of hits that have been found. But let me switch to the targets here. So let me filter just on the targets, and you can see it found the ISTDs in the blank. Alright, next let's take a look at the sample. And I've sorted on match factor here. I'm going to look at the non-targets. So it has stripped out the targets, and you can see there's heptadecane and a lot of hits from the NIST library since there's so many entries, and I've got a lot of good looking components with high library match scores. Next, let's filter on the targets, and I've come in to take a look at chloropyrifos and parathione. So looking at the entire chromatogram, if I were to see all the components that were found there and identified, let's zoom in on the parathione at 20 minutes. So here it is, and if I look at that in some detail, I can see that chloropyrifos and parathione collude. If I take a look at the spectra of chloropyrifos, I'll see here's 197, which is marked as the target ion, and you can see that there's a contribution there at 199 as well. If I switch over to parathione, you can see that 199 is also part of the parathione spectra, not necessarily part of the reference spectra. So there you can see some of the interferences between chloropyrifos and parathione. You can also see that in the shape of the component that was created. Thanks for your attention.